Dear students, in this session we are going to see a different video. Since in all my video lectures I am using MikTeX and LaTeX software to prepare the PPTs and I am mixing with Pentab to write things. But we are 80 kids. We use our own classical way by preparing the handwritten material. Most of the time we enjoy when we are students. So remembering that, I just do this video to make a comparison for zero initial velocity and non-zero initial velocity in the pen paper way. I just scan it and I'm posting to you. Okay, just we can see the wave equation in a nutshell. So when we start the problem, we use step 1. So when we do problems, we are going to compare the procedure for both zero initial velocity and non-zero initial velocity. Step 1 is going to be common for both zero and non-zero initial velocity problems under wave equation. We have to draw the diagram and we have to mention the length. As I said, even if it is given as number like 3 centimeter or 3 meter, take it as L and solve for the problem L. And the end of the problem, substitute the L value. Step 1 gets over. Step 2. Step 2 is also common for both zero and non-zero initial velocity problems because we are going to write the formula for 1D wave equation and explaining what is my A square. Next, step 3. Step 3 is also going to be common for both the solutions. Step 3 is also common for both zero and non-zero initial velocity problems. We are writing the most suitable solution, that is y of x comma t is equal to a cos lambda x plus b sin lambda x into c cos lambda a t plus d sin lambda a t, and we are going to take this as equation 1. This is common for both the type of problems. Next, step 4. Here the changes comes. Step 4, we are going to write the boundary conditions and initial conditions. As we discussed in our problem, step 1, one information, that is my diagram. Step 2, two information, that is my y double t is equal to a square y double x, and we are explaining what is mean by a square. Step 3, we are writing most suitable solution out of 3 possible solutions. So step 3 contains 3 informations and step 4 contains 4 informations, that is going to be my 2 boundary conditions and 2 initial conditions. So that's why I'm writing like this. It is very useful for you to solve the problem. Step 1, step 2, step 3, step 4. After that, what we are going to do? 1 in 1, 2 in 2, 3 in 3 or 3 star. Similarly, 4 in 4 or 4 star will give you the final solution. So that means the wave problem we are plugging into 1, 2, 3, 4 and 1, 2, 3, 4. So we'll be getting the 8 marks easily following this 8 steps. If it is a big question, then we have to find Bn and we have to substitute in the most general solution to complete this problem. I think I have given a complete roadmap for this wave equations. Okay, now let us go into the step 4. From the step 1, we can write the 2 boundary conditions. This is also common for both the kind of problems. Y of 0 comma t equal to 0 and the other end y of L comma t equal to 0. There is no displacement when t greater than 0. So these 2 boundary conditions also going to be the same. Only the initial conditions going to be changed. Now let us see the changes in the initial condition. Since it is a zero initial velocity problem, my velocity is 0. We have already discussed how to write the boundary condition. My first 3 conditions should be 0 and my 4th condition should be non-zero, that is my f of x. So in this zero initial velocity problem, so my 3rd condition is initial velocity is 0. But when you go for non-zero initial velocity problem, there is some initial velocity. So yt of x comma 0 is f of x. Here initial velocity is 0. Therefore there is a displacement at the initial time. So we are writing y of x comma 0 equal to f of x. And in the non-zero initial velocity problems, since we have non-zero initial velocity, the initial displacement is going to be 0. So in zero velocity problem, yt of x comma 0 is 0. In non-zero initial velocity problem, y of x comma 0 is equal to 0. That is the change. Now all the 4 steps gets over. Now when you go for this problem, apply 1 in 1, we will get A equal to 0. Similarly, for non-zero initial velocity problem also, when you apply 1 in 1, you will be getting A equal to 0. Then we form a new equation 2. Here also we form a new equation 2. Apply 2 in 2, that is y of L comma t equal to 0. We will be getting lambda equal to n pi by L. In both the cases, the first two conditions are going to be the same. A equal to 0 and lambda equal to n pi by L. When you go for the third condition, here zero initial velocity problem. So in this case, I cannot apply 3 because my equation 3 is y of x comma t. So now I differentiate 3 partially with respect to t to get 3 star. Now apply 3 in 3 star to get d equal to 0. But in the case of non-zero initial velocity problem, my third boundary condition is y of x comma 0 equal to 0. So I can directly apply in 3. In this situation, I get c equal to 0. So that is the difference here. If zero initial velocity problem, d0. If non-zero initial velocity problem, c0. And then once d is 0, we can find this bc. We take it as bn because further we are not going to differentiate. But in non-zero initial velocity problem, equation 4 we are going to differentiate. So I am taking this two constants which has capital Bn. Here I am taking it as small bn. Next we are going to write the most general solution. Remember students, if it is zero initial velocity problem, it is going to be bn sin cos. If it is non-zero initial velocity problem, capital Bn sin. SS. You can remember like SS. Now I am going to apply 4 in 4. Here I can apply 4 directly in zero initial velocity problem, but non-zero initial velocity problem, my fourth condition is going to be yt of x comma 0. Now I differentiate 4 partially with respect to t and I will take it as 4 star and I will apply this fourth condition in 4 star. But in the case of zero initial velocity problem, I can directly apply this. When I apply this, my cos 0 will become 1. So I am directly getting this equation. F of x is equal to summation n equal to 1 to infinity small bn sin n pi x by L, which looks like my half range Fourier sine series. So I can apply the Bn formula directly. Once I find the Bn, substitute the Bn in the most general solution to complete the problem. Now we come for the non-zero initial velocity problem. Here yt of x comma 0 is f of x. When I apply this condition in equation 4 star, I will be getting my f of x like this. Here simply I have small bn. I go for half range Fourier sine series. Here I have bn along with the other constant n pi a by L. So now I am assuming capital Bn into n pi a by L is equal to small bn. From this I can find capital Bn. Now use the formula of half range Fourier sine series and find small bn. Substitute here, we will be getting capital Bn. From this, substitute capital Bn in equation 4. That is my most general solution to complete the problem. And here there is some space in the paper. So I have filled the paper by hints. We remember sin 0 is 0, cos 0 is 1, cos n pi is minus 1 whole power n, cos 2n pi is always plus 1, sin n pi is always 0. So this is what the way we used to study when we are students. Thank you once again students for spending the time and supporting my channel. I'm very happy to see lot of comments. Share to your friends, subscribe. We'll meet in the next video. Thank you.